Alright, in today's video we're going to be talking about the laws of thermodynamics. And after watching this video you should be able to define and use the first law of thermodynamics and then define and use the second law of thermodynamics. And if you're looking for extra material or extra references to refer to, this would be found in your book on pages 326 through 331. So feel free to check those out if you wish. So let's get right into it. The first law of thermodynamics basically says that the change in thermal energy, or the delta U, of an object is going to be equal to the heat, which is represented as a Q, added to the object minus the work done by the object. And that sounds kind of confusing when you just read it verbatim, but what it really is saying is if an engine is producing heat, or heat is added to the system, how much work does it do from that heat, and then what is still the total leftover thermal energy. And all of these letters, thermal energy, heat, and work, they're all measured in joules, and so that's kind of nice. It makes calculating first law problems relatively easy. And the equation that you'll want to use is this guy right here, delta U equals Q minus W. And just a heads up, whenever you see like delta U or any delta, basically you're probably going to have a initial thermal energy, and a final thermal energy. Right? So then you'd have a UF, and this would be final thermal energy. Those are ditto signs. Okay, so just be aware that that's what that delta U is going to be referring to. So typically it's going to be UF minus UI, which is the same thing as delta U, equals Q minus W. Right? When I learned about the first law of thermodynamics, I was taught with a money analogy. And my money analogy for you guys will be basically every year on my birthday, my grandma gives me money. It's a wonderful thing, and you can do one of two things with money, right? You can either spend it, or you can save it, or you can spend some and save some. And that's kind of how the first law of thermodynamics is basically a system may get heat added to it, and it can either use that heat as work, or it can save that heat as thermal energy for later use. So let's just, for fun, let's just say my initial bank account started with $10, and my grandma gave me $20 of added heat, or whatever you want to call it. It's not really heat, but we'll say she gave me $20. And so I can add that to my U initial to get a U final of $30. But let's say I've been really eyeing a CD that I've been wanting to buy for a long time, and I decide to buy a CD, and it costs $15. I don't even know if people buy CDs anymore, but let's say you do, and it's $15. How much money do I have left in my bank account? And by the way, this $15 would be considered as work. I would have $15 left. Right. So I don't know if that makes things make sense more, but basically if you kind of look at it as your bank account, it's this thing that kind of fluctuates, where you add money to it, you take money out, and that's kind of what the first law of thermodynamics is saying. So let's look at an example problem. This might make a little bit more sense when we do an example. So first thing I'm going to do is I'm just going to write my equation here because I forgot to put it in the PowerPoint. So delta U equals Q minus W. And remember, this really is UF minus UI equals Q minus W. And that sometimes helps me just to write that out so I can see it all. It says the internal energy of a system is 45 joules. 32 joules of energy are added to the system as heat, as the system does 21 joules of work on its surrounding. What is the final internal energy of the system? And so as always, I recommend writing your knowns and your unknowns. I'm just going to change colors here so that maybe we can put my knowns in different colors, so make it a little more fun. So if I'm starting with an energy of 45 joules, that is actually my UI. My initial starting temperature, or starting energy, is 45 joules. And it says 32 joules of energy are added to the system as heat. And so that is actually my Q. I have 32 joules of energy added as heat. And the system does 21 joules of work. So my W is 21 joules of work. What is the final internal energy of the system? And that's could be represented as UF. Right? So what's the final energy of the system? And so this becomes a relatively simple problem because I'm just plugging these numbers into this equation right here and trying to figure out UF. So let's do that, shall we? UF minus U initial, which is 45 joules, equals Q, which is 32 joules, minus my work of 21 joules. And so if I do the math here, 32 minus 21 is 11. And then get UF by itself, so add 45 to this side, joules. And I get a total final energy of a 45 plus 11 is 56 joules. And so basically, if you kind of look at it like a bank account problem, basically I had $45 in my bank. Some generous individual decided to give me $32, and I spend 21 of it on, I don't know, new shoes. And how much do I have left in my bank account? Well, I have 56 joules left in my bank account, or $56 left in my bank account. So that's an example of a first law problem. Not too bad, I don't think. So if we kind of look at this as how does an engine work, like say in your car, basically what's actually happening is, in a nutshell, you are having a vapor or a liquid like gas or whatever come into your engine, and basically a small spark ignites this fuel and causes in a controlled explosion, actually, believe it or not, and it causes these pistons to move up and down. And it'd be great if this was animated, but it's not. But basically this piston moves up and down and causes your drive shaft on your car to rotate, and that's what actually makes your tires move. So when you accelerate or push the accelerator down, you're basically putting more fuel into these cylinders to cause more controlled explosions to occur, to cause the car to move quicker. The point of all this, what is this formula here? Well, basically Q is the heat, right? The total Q, and maybe I'll put that as total. The total Q equals the heat minus the heat lost. Right? The point of this is, and this isn't an equation that you'll see a whole bunch, but the point of this is to talk about the next slide, which is dealing with efficiency. No engine or any machine that man has made is 100% efficient. And this is an important component, that you just understand that nothing is 100% efficient. And so the point is, when you drive up into a gas station and you pay $3, $4, whatever it is, for a gallon of gas, that $3, that $4 does not go completely into 100% anyway, into moving your car. Some of it is lost as heat to either friction or whatever the case may be. No engine's 100% efficient. If they were, that'd be awesome. So you see this in car advertisements all the time, that they'll be talking about the miles per gallon that a car gets. Basically, we're always trying to improve the efficiency of a machine, but no machine as of yet is 100% efficient. So some of the heat created is not used as work. Instead, it's just lost to the surroundings, or it's lost to friction, or whatever the case may be. And so if you want to figure out percent efficiency, you just basically take your work divided by your Q heat times 100, and that equals percent efficiency. Again, this is a formula that won't come up that often, so I won't stress out about this that much. But the big thing that will come up and will show up later on in exams is, can an engine be 100% efficient? And the answer is no, it can't be. The second law of thermodynamics has really two important facets. One is that heat will not flow from a colder body to a warmer body. And basically what that means is heat is a form of energy. And so an area of high energy will not gain more energy from an area of low energy. And you kind of think about it, even like, just say you have a balloon, a blown up balloon, and you puncture a hole in it. what direction is the air going to blow? Well, I think we all know the air goes out, right? And the reason why is this is high pressure in here, and this is low pressure in here. And the same is true for thermodynamics. If you have say, a hot coffee mug out on your counter, this is a coffee mug, the heat is going to move from the coffee mug to the outside, where this is going to be hot, and this is going to be relatively cold. Right? So that's basically what the first part of the second law of thermodynamics is, that heat will not spontaneously flow from a colder body to a warmer body. So this coffee mug won't continually get hotter and hotter and hotter just by sitting on the counter from, like, you know, the atmosphere giving away heat to it. It always moves from areas of high to low. So I think that kind of makes sense because we see that in everyday life. The second thing is this thing called entropy. And entropy is the disorder of the universe. Basically, it's saying that things are always getting more and more disorganized, more chaotic. So basically, the entropy of the universe is constantly increasing. And so you kind of have these forms of energy. And so let's say I have like a gallon of gas. Once you use that gas and you burn it as heat, basically that heat is all over the place, right? I mean, it's all over the universe. So it was in this nice container, this gallon of gas, and now it's heat where it's everywhere. And that's basically what that's saying, is that the disorder of the universe is always increasing. It's always going from concentrated to less concentrated. And this slide here helps explain it a little bit. So the universe is always working towards equilibrium. And this picture here of basically this food coloring in water. The food coloring was dropped in where, you know, we have this little dropper bottle of food coloring, and it drops in. This is, you know, really intense yellow, right? It almost doesn't even look yellow, it's so intense. And then you drop it in, and you can see it spreading outward. This is more and more disorder. Okay, until actually you reach this point where it's really all over the place. Right? There's a formula for entropy, which basically is change in S, which stands for entropy, divided by, equals Q, which is your heat, divided by your temperature in Kelvin. That's in Kelvin. So I talked about the gasoline example in the other slide. Another example would be like your bedroom. I don't know about you, but over time my room gets extremely messy, as does my car. There'll be like wrappers in it or pieces of paper or whatever. And basically that's kind of a good example of what entropy is that if nothing cleans up, it just keeps getting messier and messier and messier. And that's kind of how the universe is. Nothing's there to clean it up. It just keeps getting more and more messy. All right, that takes care of this video, and we will see you guys next time.